All right, so very short video here trying to describe the two sampling distributions that we're going to be concentrating on. Now, and we've talked about the sampling distribution and the central limit theorem. And when we did that, we used the sample mean as an example. And I think I lied to you and told you that was the only statistic that we were going to be interested in. We are also going to be interested in the sample proportion. Okay, now I promise you these are the only two that we will be working on. So we are interested in sample means, studying those, analyzing those, and sample proportions. So like a sample mean, say we, test scores, any kind of quantitative variable that we're interested in, we are going to take samples and look at the means, those sample means, and get distributions of means, and then study that distribution to answer probability questions. We're also interested in questions concerning proportions. Like let's say I want to know what proportion of ENMU students have seen a ghost, whatever it is, right? We're going to take a sample, look at the proportion, take another sample, again, same idea as the central limit theorem and sampling distributions. We're going to get a distribution of sample proportions, and then we're going to answer probability questions about those sample proportions. So these are the two sample statistics that we are going to be interested in. The sample mean, X bar, remember, and now the sample proportion. We're going to use a P with a little carrot top arrow hat on it to signify sample proportion. P hat, we'll call it. Okay, so X bar, we call the sample mean. P hat, we call the sample proportion. Now we've already discussed this, but let's quickly review. Remember the population mean, we said was the Greek letter mu. That's different than the sample mean, right? The population mean is something usually that we don't know, right? We want to know something about that population mean. That's why we're taking samples and looking at the distribution of the samples and seeing what it looks like. And the population standard deviation was the Greek letter sigma. Now we're taking samples and getting the sample mean, X bar. We take samples of size n from the population and get a distribution of an infinite number of sample means, theoretically. And those sample means are going to be distributed normally, assuming from our central limit theorem that our sample size is greater than or equal to 30, or that the population itself is normal. If we're told that the population itself that we're taking these samples from is normally distributed, then we don't need this condition in order for this to be true. But if the population is not normal, or if we're told that we don't know if the population distribution is normal, then we need the sample sizes that we're taking to be 30 or greater in order for this to be true and in order for us to do what we want to do. So we take those samples are distributed normally. The mean of that distribution is the same unknown mean of the population. We're going to, in some of the work we're doing, we're going to say, well, I think the mean is, and we're going to use that. And we'll see that when we get to our confidence intervals and hypothesis tests. Right? But for right now, we just want to know this is the distribution with this mean and this standard deviation. Remember, the standard deviation divided by the square root of the sample size gives us what we call the standard error. I don't think I've introduced that term before, but the standard deviation of the sampling distribution of a sample statistic is called the standard error. Okay, the standard error of the mean, and that's what this is. And that's just the standard deviation of the sampling distribution. So don't let that term confuse you. If you see standard error, that's the standard deviation of the sampling distribution of X bar. And then we're going to use that normal distribution to create confidence intervals for that unknown mean. And sooner or later, we'll do something called a hypothesis test. Everything is geared toward those confidence intervals and hypothesis tests. We're going to work with means. We're going to work with proportions. And if we have time, we're going to work with the difference between two population means and the difference between two population proportions. Those are the ideas that we're going to cover in the next few weeks. So for means, sample means, we've kind of already discussed that. Now the new part here is we're going to look at sample proportions. So now we have a population proportion. We're going to call that lowercase letter p. P with a little hat on it, that's the sample proportion. So just like population mean versus sample mean, this is population proportion versus sample proportion. Okay, same idea, we take samples of size n from the population and we get a distribution of sample proportions. And those sample proportions are going to be distributed normally with the mean of the sampling distribution, the population proportion, again, usually unknown. We're going to think it's something going into our tests, and we're going to get that number. We're going to test whether the population proportion is a certain value or not. That's what we're testing because we don't know. Same thing with the means. And now the standard error of the distribution is this rather somewhat more complicated formula than for means, but no problem there. Standard error of this distribution is the standard deviation of the distribution of sample proportions. Okay? So same idea, we need the central limit theorem to apply here, and the standard error is the standard deviation of that sampling distribution. Okay? Standard deviation of the sampling distribution of p hat. Now these, I'm going to keep this video short. This is just to introduce the only two sample statistics, the sample mean and the sample proportion that we're going to be working with the rest of the way. We're going to be creating confidence intervals for means. We're going to be creating confidence intervals for population proportions. Again, because we don't know what the population mean is, we don't know what the population proportion is. So we're going to come up with an interval of values that says, well, we think that the population mean, given our sampling distribution of the sample mean, we're going to look at that and say, given this information, we think the actual population mean is within these boundaries with a certain level of confidence. We're going to say, we don't know what this is, but with the information we've gathered from samples, we can say that this value is within some boundaries with a certain level of confidence. And that's what we're going to get into next when we talk about confidence intervals.